In the rapidly evolving world of artificial intelligence, a revolutionary architecture emerged that fundamentally changed how we process sequential data, especially language. This innovation, known as the transformer, has become the backbone of modern large language models, powering everything from sophisticated translation tools to advanced chatbots. Before its advent, recurrent neural networks, or RNNs, and their variants like LSTMs, were the dominant force, but they struggled with processing long sequences efficiently due to their sequential nature. The transformer architecture, introduced in the seminal 2017 paper Attention is All You Need, broke away from this reliance on recurrence. At its heart, the transformer is designed to handle sequential data, like text, by processing it in parallel, a radical departure that unlocked unprecedented speed and the ability to capture very long-range dependencies within data. The core innovation enabling this paradigm shift is the attention mechanism. Instead of processing words one by one, attention allows the model to weigh the importance of different parts of the input sequence when encoding or decoding a specific element. This means every word in a sentence can pay attention to every other word, regardless of their distance. Structurally, the transformer follows an encoder-decoder design. The encoder's role is to map an input sequence of symbol representations to a sequence of continuous representations. The decoder then takes these continuous representations and generates an output sequence of symbol representations, effectively translating or generating text. Let's dive deeper into the encoder. It consists of a stack of identical layers. Each layer has two main sublayers, a multi-head self-attention mechanism and a position-wise fully connected feed-forward network. Crucially, residual connections and layer normalization are applied around each of these sublayers to aid in training stability and depth. Before any processing begins, input words are first converted into numerical vectors, known as embeddings. To account for the order of words, which is lost during parallel processing, positional encodings are added to these embeddings. These encodings provide the model with crucial information about the relative or absolute position of each word in the sequence. The multi-head self-attention mechanism is where the magic happens. For each word, it generates three vectors: a query, a key, and a value. Attention is computed by comparing a query to all keys, producing a score that determines how much attention that word should pay to others. These scores are used to weigh the value vectors, effectively creating a rich representation that incorporates context from the entire sequence. Multi-head simply means this attention process is done multiple times in parallel, allowing the model to learn different aspects of relationships within the data. Following the multi-head self-attention, the output passes through a position-wise fully connected feed-forward network. This is a simple neural network applied independently to each position in the sequence. It allows the model to process the information gathered by the attention mechanism further and introduce nonlinearity. Now, let's turn our attention to the decoder. Like the encoder, it also consists of a stack of identical layers. However, each decoder layer has three sublayers: a masked multi-head self-attention layer, an encoder-decoder attention layer, and a position-wise fully connected feed-forward network. The first sublayer in the decoder is a masked multi-head self-attention mechanism. It's similar to the encoder's self-attention, but with a critical difference: masking. This masking ensures that when predicting the next word, the decoder can only attend to previous words in the output sequence, preventing it from cheating by looking at future tokens. The second sublayer is the encoder-decoder attention. This is where the decoder interacts with the output from the encoder. The query vectors come from the previous decoder layer, while the key and value vectors come from the output of the encoder. This allows the decoder to focus on relevant parts of the input sequence when generating each output word. Finally, after passing through the feed-forward network, the decoder's output goes through a final linear layer and a softmax function. This layer predicts the probability distribution over the entire vocabulary for the next word in the sequence, allowing the model to select the most likely word. The advantages of the transformer architecture are profound. Its parallelization dramatically speeds up training compared to recurrent models. Furthermore, the attention mechanism effectively captures long-range dependencies, overcoming the vanishing gradient problems that plagued RNNs over extended sequences. This ability to see the big picture makes it incredibly powerful for complex tasks. The impact of the transformer has been enormous, extending far beyond its initial application in machine translation. It forms the foundation of groundbreaking models like BERT, GPT, and T5, revolutionizing natural language processing. Its principles are now being applied in computer vision with vision transformers and even in other domains, continually pushing the boundaries of what AI can achieve.